Hello and welcome to our lab on equipotentials and electric fields. Now, we're going to set up this apparatus so that we have an electric field established in this pan. Then we can use our multimeter to read the potential, the electric potential at any point here inside the pan. So, to begin with, let me sort of describe the apparatus. Now, first of all, we have this pan. Inside the pan I have this piece of plastic, but first of all I want to take this plastic grid, and this is it looks like maybe a 70 by 100 grid. I'll drop it in there and put this plastic piece on top, and then into the pan I'm going to pour some water. Now this water should be, I think, around 400 milliliters is a good amount. Make sure all my air bubbles out and everything is covered with a thin layer of water. We don't want it to be deep because we want to constrain our electric field to more or less 2 dimensions. So it'll have a third dimension of depth, but it won't really affect the shape of our field all that much. Now, in order to create my electric field, I have to have a voltage applied from one point to another. And so I'll do that using this power supply. Now this seems a little bit scary. We're putting voltage into water and then making measurements, but this is really safe. This is a low voltage. This is maybe 9 volts DC. It's like a 9-volt battery power supply. And here are the cables. One of these wires has a white strip on it, and that indicates that's the positive wire. The one without the white strip on it is the ground. And you can use this, or you can use a battery, you can use a DC power supply. So now to apply it to the water, I have these 2 electrodes. And one of the electrodes I'll call the higher voltage. So this will be around 9 volts, maybe up to 12 volts. And this voltage is ground, and I'll apply it here. So this is our ground. And now when I take my meter, this is my multimeter. Here's the common wire, so I'll attach it to the one that's already grounded. So this electrode that's grounded, I'll attach that to the common port of the multimeter. And then I have a probe here in the voltage terminal of the multimeter. And I'll dial that around to DC volts. It's the volts with the flat line across it. So we're going to read voltage, DC volts, in this pan. Now if I touch the multimeter to this electrode that's grounded, it should read 0 volts. If I touch it over here to this electrode that's at some positive voltage, it should read anywhere from 9 to 12 volts. Now in the water where we have our electric field set up, I'm going to set these electrodes a certain distance apart, and then as I can measure across, I'll watch my voltage change. The reading goes from 0 volts and progressively increasing up to 9 or 12 volts or whatever voltage this is. And so what I'm doing here is I'm reading the gradient of my electric field. You see, the electric field itself is something that I can't see. There are rules that define what the shape of that field can and can't be. Those rules are defined for you in the introduction to the laboratory. But I can't directly measure the electric field. But I can directly measure the voltage, or the potentials. And the electric field relates to the potentials, lines of equal potential. You can think about it as a topographical map. Even though you can't really describe maybe the shape of a field, if you're looking at a map, what you can do is draw lines of equal potential, or elevation lines, around, and someone studying the map can determine here is a hill. I can tell by the circular lines of elevation going up in elevation until you reach the top of the hill. So we're going to do that. We're going to draw sort of a topographical map using lines of equal potential, but these are going to be lines of equal voltage potential, not equal gravitational potential. And the way we do that is when we put our probe in the water, it may read something like 3 volts. Okay, well that's good. You've established a potential. Now, in order to get a line of equal potential, you have to find more points that are equal to 3 volts. And as I move this probe around, keeping it vertical, as I move it around, I can find other locations that are also 3 volts, and eventually I'll be able to trace out a line, and all along that line the potential is 3 volts. That's my line of equal potential. As I do this, I'm doing it on top of that graph, that piece of graph paper that I put inside the tray. Well, out here is another piece of graph paper that's representative of this graph paper in the tray. And so as I trace my lines of equal potential, I can call out the coordinates to my lab partner, and I can say, okay, at 43 and 38, I have a point that's 3 volts of potential. And so my lab partner would plot that point. And then as I go around, I'm calling out points, and eventually I have a line of equal potential graphed out on that graph paper. So if my graph paper shows the line of equal potential, it shows where the electrodes are, then as I could go progressively across, I can find a line of equal potential at 4 volts. I can find another line of equal potential at 5 volts, 6 volts. And so eventually I get all these lines of equal potential, and then based on the way that electric field lines are constrained by the lines of equal potential or described by the lines of equal potential, using those rules that are defined for you at the beginning of the lab, you should be able to infer an electric field. And so using our lines of equal potential, we'll plot what the electric field looks like, even though we really can't see it or directly measure it. Now for these lab activities, you are going to be predicting what an electric field might look like based on the electrode configurations, and then testing that to see if your predictions are correct. So our first prediction, under these electrodes we want to place these parallel plates. We have copper plates that we place parallel, and you want to trace the position of these plates onto your graph paper. Now once you have these plates in position, you can maybe try to make a guess based on the rules listed up above. For example, electric field lines are closer together where the field is the strongest. Electric field lines can never overlap each other. All right, electric field lines travel from positive to negative, and we need to show a direction arrow indicating the direction of that electric field line. And you'll make a prediction on graph paper of what you think the electric field looks like between the parallel plates, and around the edges as well if you'd like. So, and then after you've made your prediction, we'll test it. So you'll take your voltmeter and go in there and plot those lines of equal potential. Once we've plotted lines of equal potential on the graph paper, then using a different color, be sure to use a legend so we know which color is which, of pencil or pen, you will infer from those equal potential lines, the rules are, as you can read above, that electric field lines must cross equal potential lines at right angles to each other at all times. Then we can sort of infer what that electric field looks like based on the lines of equal potential and see if it matches your prediction. And then after that, we're going to take this brass cylinder, put it in the middle of the tray, and on another sheet of graph paper predict what you think the electric field would look like with the introduction of this conductor in the field. And so once you've made that prediction, then you'll go and on a fourth piece of graph paper, you will test your prediction. Now, I will tell you that you have to get really close to the conductor with your voltage probe in order to really see what those lines of equal potential are doing near the surface of the conductor. So it's a little bit tedious, but you have the entire lab to do pretty much 2 electric field configurations. So take your time and get it as close to reality as possible.